Hello everyone. Today I'll be talking about one of the source coding techniques called the Huffman coding, which is a part of many image compression schemes. So these are the contents of my presentation. First, I'll give an introduction about Huffman coding. Then we'll try to see the procedure that we have to follow to find the Huffman code. Then we'll see the efficiency of Huffman code. And finally, we will try to implement this code in MATLAB using some inbuilt functions. Coming to the introduction, the most celebrated and widely used prefix code is due to David Huffman. It was named after him and was derived in 1951. It helps in reducing coding redundancy and it generates variable length codes. So the guiding principles of the code is that symbols that occur more often will have shorter code words, which is based on the Morse principle. The second guiding rule is that the two symbols that occur least frequently will have the same length. So coming to its procedure, the steps are as follows. We sort the symbols according to their probabilities. Then we take the least probable symbols. We combine them to form a composite symbol which is going to have probability of the sum of the respective symbol probabilities. So with this step, we'll reduce the size of the alphabet by 1. So we repeat these two steps for the remaining symbols. We can see that if the size of alphabet is n, then we'll have n minus 1 stages of the procedure where each stage involves the above two steps. Finally, after we combine the last two symbols, we will arrive at a binary structure of the tree whereby assigning zeros and ones to the branches, we will get the codes for the symbols. We'll try to see this with an example. Let us take an image of size 4 cross 4 and let this be an 8-bit image. That means that the pixel values will range from 0 to 255. Let this be the matrix representing our image, and here the pixel values refers to the symbols arranged in descending order of their occurrence. Now to calculate the probability of occurrence of each symbol, we divide its frequency or the number of times it appeared in the matrix by the size of the matrix. So we can see that for 39 it is 8 by 60, which comes to 0.5. Similarly for 126 it is 0.5. The next step is to perform source reduction. We will create a table with symbols, that is pixel values arranged in descending order of their probability. After that, we'll start from the bottom and add the last two values of probability till we are left with only two values. In this case, we had only two values, so we will assign the binary code 0 and 1 to the two symbols. We can see in this table how we have changed an 8-bit code, that is a fixed length code, to a 1-bit variable length code using Huffman coding. Now we try to see how Huffman coding is helping us in image compression. For that, we'll first try to find the coding redundancy of the obtained code. So first we'll calculate the average length of the code, which is given by the formula summation of k equal to 0 to L minus 1 of L into P, where L is the length of each symbol and P is the probability of its occurrence. This comes out to be 1 bit per symbol in our case. We can also say that coding redundancy tries to reduce this average length. Also, the number of bits required to represent our image is given by m into n into average length of the code, which is equal to 16 bits. Next, we try to define entropy. So, entropy is the average amount of information obtained by observing a single source output. As its magnitude increases, more uncertainty and thus more information is associated with the source. The formula to find out entropy is given as minus of summation of k equal to 0 to L minus 1 of P into log of P. So the entropy in our case comes out to be 1 bit per symbol. Now we try to find the efficiency of Huffman code to see how effective our code is. Efficiency of Huffman code is given by the formula entropy divided by average length of the code. Since both are equal to 1, it comes out to be 100%. Next is compression ratio. It is given by the formula the total number of bits required to represent our image, which is uncompressed, divided by total number of bits required when it is compressed, which is equal to 8. Next is relative data redundancy. The formula is given by 1 minus 1 by the compression ratio, so it comes out to be 0.875. Thus we can say that 87.5% of the data in the original 8-bit image is redundant. We'll try to see the implementation of Huffman code in MATLAB. First, we store the intensity values of our image in variable I. We'll try to plot it using IMShow command. We convert it from double image having values 0 to 1 to 8-bit image with intensity values 0 to 255. Now we'll store the number of rows and column of the image in m and n variable and find the total size by multiplying these values. We use this command called unique to find all the unique intensity values that occurred in our image. The next line helps in counting the number of times the symbols have occurred. Then we try to calculate the probability. After that, we create a Huffman dictionary consisting of all the symbols with its probability. Then to perform Huffman encoding, we first convert these symbols from 2D to 1D by using reshape command. After we receive the encoded signal, we try to perform decoding and then convert the image back into a double image. Again, we use the reshape command to convert the 1D decoded sequence into 4x4 matrix and plot the transpose of the matrix. So when we run this command, this is the original image with pixel values 39 in the first two columns and 126 in the next two columns. And we obtained the similar image when we decode it after performing Huffman encoding and decoding. These are the few references that I followed for this presentation. Okay, thank you.